approximate histograms and heavy hitters using Misra-Gries sketch. Thank you, Christian.
Thank you. Yeah, as introduced, I'll be talking about our work here, which is joint work with my colleague from BAC, Jakub Tětek. So the problem of approximating the histogram should be quite familiar to most of you here. We say a histogram is just a set of counters counting how many repetitions we have of each element in a data set. And our goal here in this project is to design an epsilon delta differential private mechanism that approximates a histogram in the streaming setting. And what we want to minimize is the largest error across all of our counters. So for this crowd, I won't talk too much about how to solve this with differential privacy when we don't have to consider the streaming setting. But yeah, the nice things about histograms is that we have a low L1 sensitivity, so we can add noise from the Laplace mechanism. And in the case of approximate differential privacy, we can apply the mechanism known as a stability histogram. Yeah, and this gives us the error down here. Again, I'll just move on because hopefully at least you should be familiar with the Laplace mechanism. So instead, I want to talk a little bit about what do we mean now that we are in the streaming setting. Well, instead of having a static database or data set where we can look at everything, now our data comes in as a stream. So we get a stream of elements and we observe one element at a time. And importantly, we can only observe the elements once. The challenge that we have in this setting is that memory is very limited. So this means that our stream can be very long. And in this case of histograms, we can also have a high dimensional histogram. So there can be many different types of objects coming in. This is important because this means we cannot actually store the histogram. Otherwise, I mean, we could just, if we had unlimited memory, we could just store the histogram. Since we cannot store the histogram even without considering privacy, we can't just apply the Laplace mechanism on stability histograms because that's really the step one of these algorithms. But yeah, of course, we still want to be able to approximate this. And for now, we ignore the privacy part and just focus on the streaming part, and then the privacy part comes later again. Yeah, so if you read the title, you might have guessed that we'll be using an algorithm known as the Misra-Gries sketch. And how this sketch works is that we have a set of counters. We'll say we have k counters, where k is a parameter of our algorithm. And then we'll look through each of the elements in the stream one at a time and update our counters based on what element we see. I have a small example here where we have 3 counters. You can see the next element we see is a B. In the top example, we already have a B, so we just increase that counter. In the middle, we don't have we are not counting how many Bs we have, but we have room for one more counter, so we just create a counter for Bs and set that to 1. Those sort of the simple cases. The most interesting case is the last one. Here, all the counters are full, so we cannot count the Bs. So what we do instead is we decrement all of the counters by 1. And if any of them hits a 0, then we throw that out. So at some point, if we keep using this process, there will be room for Bs. So if the next element was a B, now we would have room for a counter. Yeah, and this algorithm is used at how much error do we have in this algorithm, right? Because that's what we really cared about in the end. What's the largest error among all of our counters? And from the last slide, we have these 3 cases, and you can observe that the 2 first one doesn't introduce any error. The last one where we decrement all the counters, that's the one we care about because that introduces some error. But you could do some analysis, and then you see this can't happen too often because at a certain point the sketch will be empty, and then we have to fill it up again. So it happens at most, across the stream, it happens at most every k+1 step on average. So this means no matter what stream we are working on, our error will be at most n, which was the length of the stream, divided by k plus 1, again, k being the size of the sketch. So this is the parameter we work with. So the bigger the sketch, the more accurate we get. But of course, there's a trade-off, right? At some point, we don't get a lot of accuracy and we have to use more memory. And now you might ask, well, is this good or not? And this is actually the optimal for any mechanism that outputs k elements. And you don't even need to know anything about streaming algorithms to see this, because in the case where k was 3, so we have to output 3 elements in the end. If we have a data set where we have 4 distinct elements, which are each present n divided by 4 times, then we'll have to remove one of them. So no matter which one we remove, we get this error. So the sketch is very nice in that it's quite simple, and it achieves the optimal worst case error. And for some data sets, it performs better than this error. Okay, so this sketch is very nice in the non-private setting. We know in the private setting how to solve the problem of approximating a histogram by adding Laplace noise. Now, what we want to do is to try to merge these two domains of the streaming algorithm where our space is limited and the differential private algorithm, the differential privacy regime, of course. So yeah, that's our task. So the first thing we need is a neighboring relation. We say that 2 streams are neighbors if we can obtain one of them by removing one of the elements from the other one. And yeah, then our task is to design a private version of this sketch. And we are not the first people to come up with this idea. So prior work has shown that the L1 sensitivity of this sketch is k, again with k being the size of the sketch. So this is great news because then we can apply all sort of our standard techniques for how to make these things private by adding Laplace noise, so on, and then we end up with the error that you can see down here. But now the problem is that we have k. Yeah, we have to scale the noise up with k. So this means if we want the sketching part of the algorithm to be more private, then we'll have to increase k. But that means that we'll have to add more noise because now our sensitivity goes up. So we really want to see if we can do something better. And yeah, that's exactly what we'll do. So in order to do this, we have to look a little bit closer at the structure of this sketch, specifically the structure of between 2 neighboring sketches on neighboring streams. The first thing that can happen is that a single count differs by 1. And this is really, you can think of this as an easy case, right? Because this is similar to what happens in just a histogram when we don't have to care about all these memory limitations. So this is sort of the easy thing. The more difficult case is when all of the counters, they can also differ by 1. And this happens when this step where everything decrements is performed once more for one stream than it is for the other. And this here you can also see how they ended up with this L1 sensitivity of k, right? Because we have k counters and each of them differ by 1. So that means our L1 sensitivity is k. But now we really come to our core idea of what we want to do. So here on the left, I have an example with where k is 4. You can see what happens when we have k sensitivity of 4. Then there are all kinds of different inputs that that has an L1 distance less than 4. So when we are designing a differential private algorithm that protects against L1 sensitivity of k, then we're really protecting against all of these different types of changes between neighboring sketches. However, as we saw, in our case, we actually know that most of these situations will never occur because we know we'll always end up in one of the 2 cases. So instead, we'll try to target the two cases specifically instead of having this more general setting. So yeah, how can we do that? Well, yeah, the first thing we'll do is yeah, we just compute the sketch as before, and this gives us some counters over here, and nothing special here. The next step should be familiar. What we do is we add noise sampled from the Laplace distribution with scale 1/epsilon to independently to every counter. So this is very similar to what you should know from the Laplace mechanism, and this this step really targets the first case, right, where a single counter differ by 1. So this is really to target that one. Now the next step will target the other that will target the other case. What we do is, again, we sample from the Laplace distribution, but what we just sample a single value, and then we add that same value to all of the counters, because this step where all counters differ by 1, this means that we can really hide that by adding noise to all of the counters at once. So we really offset everything in the sketch. Yeah, so now we have these two different types of noise. And the last thing we need to do is we remove all of the noisy values that are below some threshold. So if you're familiar with how stability histograms works, this is the same idea that because the two sketches might differ in which elements are non-zero, then we have to remove small values in order to hide the difference in keys. So we have these 4 steps, and yeah, one targets this case where we differ in one element, and the other one targets the other case. So by targeting these very specific cases, we don't have to resort to this general L1 sensitivity or L2 sensitivity for that matter. Okay, so what are our error guarantees? Well, there were these different steps of the algorithm. We have some error coming from the sketch itself. Then we have some error from the Laplace noise, but in this case, that's really dominated by the error from the threshold. So the expected error for any input will be less than n divided by k+1 plus O of log 1/delta divided by epsilon. Yes. So now the algorithm I showed you here only works for approximate differential privacy. But sometimes we really want pure differential privacy, so we want delta to be 0. I'm not going to talk about how to do that, but you can talk to me at the poster session if you want. But we can do that as well and get error again with the error from the sketch, but now with log d over epsilon. You end up adding twice as much noise as for a standard histogram. So to summarize, what have we shown here? Well, we have a lower bound for how much error we are required, or there will be for worst case input if we have to achieve differential privacy. We have another lower bound saying how much error we have to achieve if in this streaming setting when we have a size of k, and our error basically matches the sum of these two terms. So that means our error in the end is optimal up to some small constants. Yeah.
I think we have time for one question. Do you have any questions?
Yes. So actually, that's. Oh yeah. The question was, our algorithm works with one-shot output. And the question is now what to do if it's continuous output. And actually, the previous work here worked on that setting specifically. So they compute a sketch, and then they have a structure that's similar to the binary tree mechanism, where you compute a sketch and then you compute a new one and a new one and a new one, and then they sum those up. So what you could do is take their work and then replace their version of the sketch with ours, and then you would just get this improvement in K again. So you would end up having to compute multiple sketches, right? So you'll have some size, and say you compute a sketch for the next I don't know, 10,000 elements, and then you have a new sketch every 10,000 elements, and creates something that's similar to the binary tree mechanism. So that's not really a focus of what we are doing, because the previous work did all of these things. So we can just take their sketch and replace it with ours.